Wish I hadn't done that. Physical science time. Okay, today we're talking about atoms, or let's call it elements. The properties of elements, that's a good word. The properties of elements. Why is this important for us to learn about? Cyrus? Why do you think this is important for us to learn about? Yeah, why do you think it's important to learn about the properties of elements?
Except what the elements are.
Okay, yeah, it's the stuff that tells us what the elements are. That's important. Why though? Why is that important to your little life? It's not wrestling. Why is it important?
We know how to use them?
Probably that won't come up. You mean like in case the devil pops up out of hell and gives you a piece of cesium, you can be like, "It's cesium, please let me go," or something like that. Is that what you're talking about? That would be useful if that did happen. But
yes,
this isn't an anime, is it, Jaden? So.
So.
Okay, yeah. So if you had like a sample of something and you were worried about mishandling it, perhaps, you would know some of the properties so it wouldn't blow your face off.
If you're going to be a scientist.
If you're going to be a scientist, if you want to go to the science factory and sign up one scientist job, please, and fill out the application and go to work, yeah. No, or science teacher, like some of these other idiots, yeah. No. Okay, so for one thing, there is some value in pure knowledge. Like, you're made out of this stuff, right? So it's interesting, or at least it should be interesting, to know that these kind of things are happening all around us. The stuff that the world is made up around us is made of this, and so that's important. But also, I think more deeply than that, the principles that govern the properties of elements are kind of things that are true of the whole world. There's an overlap between this and the way, in English, the way these characters act in the book. I mean, the critical thinking that is required for you to understand and to use this and do a good job on it also applies to the other things in your life. So let's begin then. We had talked in the last chapter about the periodic table. Do you remember that? Let's draw another periodic table here. This is really good if I do say so myself. I'm getting good at this, drawing of periodic tables. Who sarcastically wowed? Justice, don't do that.
It was a good
Please draw a periodic table. What do we call this? Have we talked about this? We almost exactly did this same thing in chemistry a while ago, so I can't remember. Did we talk about this? Do you remember this thing?
Yeah.
What's that called?
The
Stair-step line. Okay, we did talk about it.
Yeah.
Stair-step line. And what does the stair-step line divide?
Like metals.
With the metals and
non-metals.
Yes. So everything relative to the stair-step line, the things on this side, the left, the port, are what?
Metals.
Metals. All of this. I should have drawn a better symbol. This little catch-all symbol. And then everything on this side of the stair-step line are? That's interesting you say that, because Lavoisier and Priestley would have called them airs, yeah. Not all of them, but they're all, we call them...
Gases.
No, they're not all gases.
Non-metals?
Non-metals. Non-metals. Many of which are gases. And then the things that touch the stair-step line, except aluminum, the things that touch the stair-step line are metalloids. And they're not a mixture of different elements. They are elements, but their properties are a combination of the properties of metals and non-metals. So those are the three broadest categories of areas of the periodic table. There are the metals, the non-metals, and the metalloids. Is it a coincidence that, do you remember we had a little rule that group 1 has how many valence electrons? 1. Group 2 has 2, etc. 3, 4, 5, 6, 7, 8. Right? Remember that? Do you think it's a coincidence that that was true and that's how it's organized and that this is how the metals and non-metals are? Do you think that's a coincidence? No? So what is it? What must be true of all of these metals? They all have...
Same.
Okay, well, let's start with the non-metals. How many valence electrons does this non-metal have? 4. And this one has?
5.
So all of these non-metals have between 4 and 8 valence electrons, right? All of these metals have then between 1 and 4. Yeah, some, like this one would have 4, it's a metal. So So is it a coincidence that the number of valence electrons matches that? So there must be something about how their valence electrons are that makes them a metal, right? There must be something about how their valence electrons are that makes them a non-metal. Let's start with that. So metals, I'm going to draw a little chart here. We're going to have a little, oh, I don't want to do it in black. I want to do it in purple. Where's my purple at? Here we go. We're going to have a little chart here. We're going to list some properties of metals, some properties of non-metals, and then we're going to just remember that metalloids can have some or many of each kind of those properties. So let's start with the one property. This is not something we could observe, but it's one property that we just talked about. Metals generally have how many valence electrons?
1 to
1, 2, 4.
Yeah, and this is kind of, I'll put a little about sign. I know this is not a hard and fast rule, but 1 to 4 valence electrons. So the nonmetals would have about 4 to 8 valence electrons. The reason that one I put first and why it's important is because the number of valence electrons, remember, does what? What does that tell?
what element it is?
No, the number of protons determines what element it is, but the number of valence electrons determines how it, what verb? Yeah, it does determine the charge, but that even that tells something about how it does what. Very important thing for the next chapter.
How it reacts.
Yes, exactly. How it reacts. Thank you. How it reacts. And that's chapter 20 is chemical bonds, which is going to talk all about how reactions occur, how these things react together. But this is important here because these tell us how it's going to react, which are its what kind of properties? Chemical properties, exactly. So this basically, this number here, this number of valence electrons is telling us its chemical properties. Chemical properties. I wrote that very tiny, and I'm going to put it over here too. So the chemical properties are told by the number of valence electrons. What are some other properties of metals, do you reckon?
Hard. No.
Okay, hard, usually. Always? Not really, but they usually are hard, and what else?
Usually solid.
Shiny, yeah, I like shiny. Almost all of them are solid. Hard, shiny, solid, what else? Remember, your book had some...
Sharp.
They're not always sharp, but your book had some...
Malleable.
Yeah, your book had some vocab words that I want you to apply to this. Malleable, what's that mean?
It means like bendable.
Which means they...
Yeah, it comes from the Latin word malleus, which is the word for hammer, which means that it can be pounded into thin sheets. If I took... Can I take this?
Yeah, sure.
What's in here? What's this? What's this? This is...
Water bottle.
Yeah, this is Fossil's water bottle. If I took the water inside of it, just the water, not the bottle, just the water, if I had a floating cylinder of water here and I hit it with a hammer, would it be malleable? Could I hammer into a thin sheet? No, the hammer would go through it. It's a liquid. What about the plastic itself? If I hammered that, would it bend into a thin sheet?
Yeah.
No, it'd probably break. What if I had some glass? Would that hammer into a thin sheet? No, it'd break. But if I had some metal, so metals have a property where if they get hit, they will retain the shape as when they got hit, which is that's not everything is not that way. You know, like there's a lot of stuff that'll just break when it gets hit. So malleable is important. What else? There's one that goes with that. Ductile, yep. And ductile means that it's the same reason. It's because they can move around, the atoms can move around without falling apart, and that allows it to be drawn into a thin wire, which is important, obviously. A lot of what we do with metals has to do with wires.
Some are brittle.
Some are brittle. We could put that in here, I guess. I'll put it in cursive. Some are brittle. There are others that are tough, but what are some properties of nonmetals then? Usually we put brittle in this category. If they're solids, they're either brittle solids, or what else can they be if they're not solids? Gases. If they're solids, they're dull, they're not shiny. They're not malleable or ductile. And then what do you reckon of metalloids? What properties would they have?
Like a mixture of both.
Yeah, a mixture of both. A mixture of both. Each individual metalloid would have some properties of metals and some properties of nonmetals, and another metalloid might have different combinations of those. So they'd all have some properties of metals and some properties of nonmetals. Okay, so we're going to now, and you will have already done this in your lesson review. But before we move on, let's talk about, because the book does not, the next chapter is called bonding, but for some reason it does metallic bonding in this chapter, and this is on your test. So we're going to label this thing here. Let's draw this diagram, the sea of electrons. This is the way metallic bonding occurs, so let's write that down. Metallic bonding. I cannot distinctly remember if this diagram and how it's used is on your test for chapter 19 or for chapter 20. And the reason I can't remember is, for one thing, I think it should be on the chapter 20 test, but it is in your book for chapter 19. And the other thing is that chapter 20 is about bonding, and this is obviously a type of bonding. So don't be surprised if it isn't on this test. And also, I just told you, if it isn't on this test, when will you see it again? Chapter 20. So just be careful that you know about this, okay? I know it is, one of your long form answers is diagram the sea of electrons and explain how it works, or something like that. So anyway, we have these atomic nuclei of metals, kind of like islands in a sea. And they can be, they're not always, but they can be crystalline, which means they have a repeating pattern, which is kind of what I'm trying to draw here. And they're kind of like islands in a sea. And these are nuclei, right? So they're protons and neutrons together. But what charge would these have if they're the nucleus? Positive, yeah, it's positive because it's protons and neutrons. So these have a positive charge. Don't confuse my drawing. This is the exact same thing I drew for just protons, but each of these is a little pile of protons and neutrons. They're atomic nuclei of a metal. So for instance, if this were sodium, each of these would have, maybe if it was sodium 23, say, they'd each have 11 protons and 12 neutrons. But all together, that's a positive charge, right? Because their electrons are dissociated, that's what we say. Their electrons are dissociated. Each one of these, instead of having valence electrons that are captured by each atom, they just kind of share. All the electrons are shared among all of them, like communism.
Yay.
You know in communism how...
They also starve.
Yeah, these guys aren't starving though because they don't need food. But the electrons are shared among all of them. That's what gives these properties to the metals. They're bonded in this way, and so they're hard because these bonds are relatively strong among them. It has a crystal lattice for one thing. They have a pattern of atomic bonding, and the bonds are relatively strong, and so that makes the substance hard. They're shiny because this tends to form a flat surface, which is what makes things shiny. It's solid, just not always for one thing. Mercury's not solid, but this would be solid because of the strength of the bonds also. And it's malleable, which is kind of interesting because if you imagine I hit this with a hammer, in the case of a plastic or glass or something like that, the hammer would break it because the bonds would separate. But in this, the bonds are kind of mobile. The electrons are flowing around, and so if I hit it, it just bonds with the next guy instead. So that makes it malleable and also ductile. Okay, some of them are brittle, but those brittle things are usually nonmetals. Or metalloids, actually. So this sea of electrons, it also gives it another interesting and unique property, a couple of other ones. Because these electrons can flow so easily, what do we call the flow of electrons? Do you remember?
Power.
Not power, necessarily. That's too broad. Electricity. So because the electrons can flow so easily, these are good conductors of electricity, and because they can flow so easily, they're also good conductors of heat. So this flow of electrons, because if we focus on this little guy up here, this electron right here can easily flow. He's not trapped with this person. He can easily flow all the way over to here, and that would be an electrical current if the electron moves. It's an electrical current, and also the transfer of heat can happen from here to here because the electrons can move so easily. What's this entire model called? The sea of electrons, and it applies to what kind of things? Metallic bonds, yeah, metals. You have questions about that? Okay, the last thing we're going to do, and this might take a while, but it's the last thing we're going to do. We're going to name these individual groups of atoms, and you kind of need to be responsible for knowing what. You don't have to memorize the periodic table, but you need to be responsible for knowing roughly certainly where the groups are found in the periodic table, and what elements are vaguely in a group. Like if I say barium, you should know that barium is a metal, for instance. But anyway, we're going to start with group 1, and you should label these. Do you have a diagram here? Maybe it'd be easier if we wrote them out. One is called the alkali metals. Alkali metals. And you can write down some properties. There's a lot of information on the internet about alkali metals, but alkali metals have how many valence electrons? They're in group 1, so they have one valence electron. What property do you think that gives them? Well, how does this relate to bonding? Do you remember? What do they all want? What are they all most stable with? Did we talk about this?
Yeah.
Yeah, how many electrons are they most stable with?
The one.
No. Maybe we didn't talk about it, but and we will in chapter 20. But there's this idea of the octet rule where they're the most stable if they have 8 valence electrons. How many is the most they can have? 8. We did talk about that then. So the most they can have is 8, and they're also most stable with 8. So if these ones all have 1, what can happen to make it so they have 8 instead? Well, if you're doing it straight up mathematically, you can think they need to gain 7. But that's probably not the easiest way for them to do it. If you're potassium, number 19, what could you do to have a full valence electron of 8? You only have 1 valence electron. What could you do with it?
Goes through.
You only have 1 valence electron in your outermost shell. But if you got rid of that 1, now your new outermost shell would be the next one down and it would be full already. Do you see? So these ones are very reactive because they are very close already to having their octet rule satisfied. And so these are extremely reactive. Very reactive. In fact, these are the ones that you've seen on YouTube probably if you're a violent person, where they take just a piece of sodium or potassium or something and put it in water and it explodes. It'll make a literal explosion because it reacts with the water so fast. And we'll do that in the lab if you want. But these are extremely reactive and they're called alkali metals. The reason they're called alkali, have you heard the word alkali before?
No.
What does that mean? So if you think about maybe east of the lines, there are something that people call alkali lakes. My dad worked on the railroad and when he would say that those lakes, they're more like wetlands really, that if a cow died and fell in one of those, its body would dissolve in a month because of how alkali it was, or how what we can say in science is basic. Because they generate these, it's kind of the opposite of an acid actually, maybe not the opposite, but it works the same way as an acid almost. It's very reactive, but they form alkali, like bleach is an alkali, lye, which makes up soap, is an alkali. Anyway.
Is that like, you know, put the little stuff in the water, it turns the color?
Yeah,
And then the more like
That's-
bluish purple it is, the more alkaline.
Yeah, the universal indicator, yeah. But they're called alkaline metals because when they combine with water, they form these hydroxides of like sodium hydroxide or potassium hydroxide. And we'll talk more about that certainly when you're in chemistry, but also probably in the next chapter, so, or maybe 21, I can't remember. So anyway, group 1 are the alkaline metals. They're very reactive. Group 2 are the alkaline earth metals. The way that you can remember the difference between these two is group 1 has one word before metals, alkali, and group 2 has 2 words, alkaline earth metals. These are slightly less reactive because they have 2 valence electrons, so it takes a little bit more energy to remove their valence electrons. But they're still really quite reactive. Then groups 3 through 12, I'll do these two in pink. And then I'll do groups 3 through 12 in purple. It'll be like a rainbow. Groups 3 through 12 are called the transition metals. These are the ones you're probably the most familiar with as pure elements, things like iron, nickel, copper, gold, silver. You know about those things. Those are the metals you're familiar with, and those are transition metals. And that's in this group here, transition metals. What comes next? Blue? Group 13. How many valence electrons does group 13 have? 3. Group 13 is called, usually I just call it the boron group, but there is the fancier name for it that people rarely use nowadays is called the icosagens. We're probably not going to talk about it. I'll put it up here, but we usually just call it the boron group. Your book goes into detail about some of the properties of the elements that are within it, which is interesting, and some of those might be on your test, so I would be sure to read it. Especially aluminum I want to focus on for a second. Aluminum's in this group, and aluminum has 3 valence electrons, but also, even though it's touching the stair-step line, aluminum is the only one touching the stair-step line that is a metal. It's not a metalloid, even though it's touching. It's a metal. I mean, you know about aluminum. You know about aluminum foil. There's aluminum foil right over there in the corner. Also, gallium's kind of interesting because gallium will melt in your hand. I should have kept that a secret because we sometimes do this. I haven't done it with the freshmen for a long time because they make a mess every single time. But gallium is a metal that has it's a solid. If I put it in your hand, it's a solid. But if you hold on to it for long enough, it'll melt just with your body heat. And indium's kind of interesting because I saw a YouTube video of Vsauce telling me that indium is the only element on the periodic table that you can take a bite of. I don't know if I believe him or not. I think it is mildly toxic, and there are lots of non-toxic metals, but you couldn't bite one. They're too hard. But indium you can take a bite of, and ostensibly, according to Vsauce, it wouldn't kill you. I'm not willing to try it. Anyway, so that was 13. The boron group is 13. The next one over is the carbon group, which we sometimes, once again, the fancy word for is the crystallogens, but we usually just call it the carbon group. Oops. This marker not good. Yeah. See ya. Thank you. 15. Carbon is extremely important. Back to 14 for a second. Carbon is extremely important because of how many, it can form bonds with lots and lots of different things. It can form bonds with itself to make huge chains. Your body, all the important parts of you that make you a living thing and not just a pile of mush are carbon. The carbohydrates, the lipids, the proteins, those are all dependent on the element carbon. A lot of times in biology, you might be called a carbon-based life form because the bonds that make up who you are carbon-based. 15 is the nitrogen group. This one, quite a bit more commonly, we do call the nictogens. I wrote this word that you actually need to know how to spell in the color you can never see. The word is spelled P-N-I-C.
The what?
The word, nictogen. The name of this group. P-N-I-C. T-O-G-E-N. P-N-I-C-T-O-G-E-N. Nictogen. The next group is the oxygen group, which even more commonly now, we do call this the chalcogens. In fact, I would say this is the first one where we call it the chalcogens more often than we call it the oxygen group. So this is group 16 is the chalcogens, which I've done in the same color as metalloids, sorry. I don't have to tell you about the importance of oxygen. Oxygen is an extremely important element. And then 17 is the halogens. And you're familiar with some of these, I'm sure. Chlorine, you know about chlorine because it's in the swimming pool. Iodine, you know about that because you probably had it on a cut at some point in your life. You might have heard of bromine or fluorine. 17 is the chalcogens. C-H-A. Oh, sorry, 17 is the halogens. Halogens. They're called that because the words are kind of archaic, but chalcogens is called that because they were thought to make up chalks, like you know what chalk is. Yeah. And then halogen is called that because they make up salts, and that is true. They do make up many kinds of salts. And then we'll call, I wish I had a different color besides black and brown left. Brown it is, I guess. 18 we call the noble gases. And we call them that because they already have 8 valence electrons, which is how many they want, and so they do not react. Just generally not reactive at all. The noble gases are, this one starting with helium and going down. Just to repeat, you will be responsible for knowing several of the kinds of elements in here and the properties. I just wanted to name them for you so you know that this is a good start. And on your test you'll be expected to certainly know the names of these groups and how many valence electrons they have. And you should also be somewhat familiar with the elements that are in them. Okay? Do you have questions about that? One last thing before we go. You had a vocab word called a diatomic molecule. Does anyone want to help me remember what that is? What's a diatomic molecule?
It consists of 2 atoms of the same element.
Yeah, 2 atoms of the same element. So there are diatomic molecules, and there are 7 of them. They are hydrogen, nitrogen, oxygen, chlorine, fluorine, bromine, and iodine. And these should all be H2, N2, O2, Cl2, F2, Br2, and I2.
Is that first one hydrogen?
Hydrogen, yep. let's mark them on the periodic table. Where's hydrogen at?
Number 1.
Yep. Here's hydrogen. What about nitrogen?
It's
Right here.
right there.
Oxygen,
Right next to it.
fluorine, chlorine, bromine, and iodine. The reason I mark this is because how many are there of them? 7. And so there's hydrogen, and this kind of looks like the number 7, right? Do you see what I'm saying? This is kind of a good mnemonic to remember which ones are diatomic. The reason this is important is when we get to chemical reactions, in the next chapter into chemical bonding, and especially when you're in chemistry, if a chemical reaction says hydrogen plus oxygen, it doesn't mean H plus O, it means H2 plus O2, right? Does that kind of make sense? And that, of course, that makes water. But even like if your granny's on oxygen, or if you've gone scuba diving, you need oxygen, the tank will say O2. Because oxygen just has one single atom, doesn't really exist very often. It always combines with itself to form O2. Same thing with hydrogen and all these other ones. Questions about that? Questions about how the periodic table is organized? Do you see how, I mean, this is like the 3rd video in a row where we've just talked about the periodic table. What's really fascinating about the periodic table is that it's organized in such a way that we can get so much information out of it. We know obviously that the order of these represents how many valence electrons they are, but that also in turn represents how they react, which is extremely important about them. And so I say that this is the pinnacle of human organizational achievement. Like, this is the best organized thing I've ever seen in my entire life. It just works so well. Questions? Questions about sea of electrons? Questions about the types of elements there are? Will you be able to have these memorized, do you think?
Possibly. Yeah.
Possibly. I hope so.
One.
Questions about the difference between metals and nonmetals? Okay.